Okay, so I want to go over integration by substitution, section 5.5. So if you recall, integral of cosine x dx equals sine x plus c, because the derivative of sine is cosine. So what if I wanted to say do integral of cosine 2x dx? So which function has a derivative of cosine 2x basically? In this case, we will use what we call U substitution, which is based on the chain rule for derivative. Remember the chain rule, derivative of f of g of x, derivative of a composite function, you do the derivative of the outer function at the inner times the derivative of the inner, which means the integral of f prime of g of x, g prime of x dx equals f of g of x plus c. And if you look at, we can let u equal g of x, and if you do that, then du by dx is g prime of x, or du is g prime of x dx. So all this is du, and this would be f of g of x, but g of x is u, so f of u plus c. So look what you have. You have integral of f prime of u du, antiderivative of the derivative, it's going to give you the original function plus c. That's basically the U substitution rule. Sorry. So here's the U substitution rule. The U substitution rule. We skip all the introductions. So if you're doing integral of f of g of x, g prime of x dx, that's big F of g of x plus c, where big F is an antiderivative of little f, which means the derivative of big F is little f for all x in I, where I is the interval where f has a range, belongs to I, or it's I itself. Basically, you're gonna say u equals g of x, so this is du, and you get f of u plus c. So for example, if you want to do integral of cosine of 2x dx, you let u equals 2x, so du by dx is 2, so du is 2 dx. So this would be cosine, so this is following this, cosine of u is 2x, and dx, it needs a 2 to become du, so if you times by 2, you're going to divide by 2, so you put this outside. Now you have 1/2 the integral of cosine u du, which is 1/2 sine of u plus c, but remember what u is, we made it up, it's 2x. So if you find the derivative of half sine 2x plus c, it's going to be cosine of 2x. And there are steps that we followed. Let's go over those steps. Here's a handout, it's inside the notes. So steps for U substitutions: choose u equal g of x, usually choose u for which du is g prime of dx is already part of the integrand, or it's a constant. Okay, compute du by dx, rewrite the integrands in terms of u and u only. At this point there shouldn't be an x in the integrand. Evaluate the integral in terms of u, and then go back and replace u with g of x. Add a constant to your answer. Okay, so here's an example. How do we integrate x squared times x cubed plus 5 to the 4 dx. Some students on tests, they actually work this out, multiplied it 4 times by x squared, then integrated. That's crazy. What if this was to the 40th power? So you're gonna use u substituting by letting u equal the inner function, because you will see why, because du by dx is 3x squared, so du is 3x squared dx. So you already have x squared dx part of the integrand. All we're missing is the 3, so we times by 3 and divide by 3 on the outside. So all this is du, and we got u to the 4 and the 1/3 on the outside, and everything is u, no x, so it's 1/3 integral of u to the 4 du. Using the power rule, this would be 1/3 u to the 5 over 5 plus c. So that's 15 at the bottom. U to the 5 is x cubed plus 5 to the 5 plus. Here's another example. Example 2. The integral of cosine x, sine of x plus 2 to the power 5 dx. Again, obviously, because the derivative of sine x is cosine, so we're going to let u equal sine x plus 2. So du by dx is cosine x. We already have that, so du is cosine x dx. So we have u to the 5th, and that's all du. So the integral of u to the 5th du using the power rule, this is u to the 6 over 6 plus c, which is sine x plus 2 to the 6th power, because u is sine x plus 2 plus c. Okay, example 3. Integral of u squared square root of u cubed plus 2, and you can see we're always picking, so I'm going to use t instead of u. Okay, so let t equal, we're picking the t or the u usually with the higher power, because when you find the derivative, dt by du in this case, it's 3u squared du. So we got that, v3. All this is going to be dt, and then this is t, so dt is 3u squared du. So this would be the integral of t to the 1/2 dt, so t to the 3/2 divided by 3/2 plus c u cubed plus 2 to the 3/2 plus c. And I forgot to put the 1/3 here, so you're gonna bring the 1/3, so it'll be 2 over 9. Please fix that. So example 4, integral of x cubed over square root of 1 plus x4 dx. Again, we let u, which is the highest power, 1 plus x4 equal u, so du by dx is 4x cubed, so du is 4x cubed dx. We already have x cubed dx, we're missing a 4, so to make up for that, we divide by 4. So it would be 1/4 integral 4x cubed dx is du, and that's square root of u, so u to the 1/2, we bring it up to use the power rule, u to the negative 1/2 du, so 1 over 4, we add 1 to the negative 1/2, we get 1/2, divide by 1/2, or timesing by 2 plus c, 2/4 is 1/2, u to the 1/2, that's square root of u is 1 plus x to the 4 plus. Okay. Example 5. integral of x sine of x squared dx. So we let u equal x squared. So the derivative of u with respect to x is 2x. That means du is 2x dx. We already have x dx. Needed 2, 1/2 to make up for that. So this would be 1/2. All this is du, and this is u. So we get integral of du sine u. And we know the antiderivative of sine is negative cosine plus c. Pull the negative out. Cosine of u is x squared plus c. Example 6, integral of x plus 1 e to the x squared plus 2x dx. So if we you can let ux plus 1, but it's not going to be good because we need to get rid of that. So u equals x squared plus 2x. Du by dx is 2x plus 2. Du is 2 times x plus 1 dx. I already have x plus 1 dx. I need a 2 and 1/2. This is du, and that's u right there. So I would have 1/2 integral of e to the u du. E to the u is e to the u plus c. So e to the x squared plus 2x plus c. Okay, a lot of applications. Next one, integral of square root of tangent x secant square x dx. So if we let u equals secant, derivative of secant is secant tangent. We don't have that. If we let u equals tangent, derivative is secant square. We have that. So u is tangent x. Du by dx is secant square x, which means du is secant square x dx. So all this is du, and this is u 1/2 square root of u. So it will be integral of u to the 1/2 du, which is u to the 3/2 divided by that, or times the reciprocal plus c. So it's 2/3 tangent x, which is u to the 3/2 plus c. Okay, next one, the integral of 2e to the x minus 2e to the negative x over e to the x plus e to the negative x squared dx. So it looks like we're going to let u equal the bottom and see what happens. All this, because that's going to give me 2, so let's hope this is going to work. So if we let u equals with the square, okay? I meant this without the square, so square does not do with it. So u equals e to the x plus e to the negative x. So du by dx is e to the x minus e to the negative x. Well, I have a 2, so I'm going to factor the 2 out there. E to the x minus e to the negative x dx. So all this, if you write du, it's e to the x minus e to the negative x dx. So all this is du. So all this is du. And what do I do with the 2? Just bring it out. And so I would have the 2 out. Integral on top, it's du. On the bottom, it's u squared, which we're going to move up to do the power rule. So 2u to the negative 1 over negative 1 plus c, negative 2 over u plus c. So it's negative 2 over e to the x plus e to the negative x plus c. Okay, Now for something like this, don't let anybody trick you. Integral ln of e to the 2x minus 1. You don't need any substitution. These cancel out. Integral of 2x minus 1 dx, which is integral of 2x minus integral of 1 dx. So it's x squared over 2, which is x squared minus x plus c. Number 10, integral of 3 minus x times 7 to the 3 minus x squared dx. So if we let u equal the more complicated expression, so du by dx is 2 times 3 minus x to the first power times derivative of negative 3 minus x is negative 1. So du would be negative 2 3 minus x dx. 3 minus x dx, we're missing a negative 2 times by negative 1/2, and this is u. So it would be negative 1/2 integral of 7 to the u du. And we have the rule for a to the u. Integral of a to the u is a to the u over ln of a plus c. So it's negative 7 to the u over 2 ln of 7 plus c. Negative 7 to the u is 3 minus x squared over 2 ln of 7 plus c. Okay, number 11, integral of x plus 1 root 2 minus x dx. It looks like if we do u equal this, there's no derivative, it's 1. So what makes sense, we're going to do the 1 under the square root as usual and see what happens. So du by dx is negative 1, so du is negative 1 dx. So we need a negative 1. So we need a negative 1 here to make up to that. This is du, and this is u, but we still have x plus 1. We gotta get rid of that. So we're gonna use right there what we did for substitution. If u equals 2 minus x, that means x is 2 minus u. So we're gonna take this and put it in there. 2 minus u plus 1. So what do we end up with if we did that? We're gonna get negative integral 2 minus u plus 1 is 3 minus u, square root of u, or u to the 1/2, and then du. And then we're going to distribute, so we're going to get negative integral of 3u to the 1/2 minus u to the 3/2 du. So we're going to integrate, pull the negative out, so negative 3 u to the 3/2 divided by 3/2, so times by 2/3. Negative and negative is plus. U to the 5/2 times 2/5 plus c. So it would be negative 2 u to the 3/2, which is 2 minus x to the 3/2. It's 2/5, 2 minus x to the 5/2 plus c. It's a little bit trickier than all the other ones. Okay, let's do one with definite integral. Integral from 0 to 2x over square root of 1 plus 2x squared dx. So obviously u is the bottom, 1 plus 2x squared. So du by dx is 4x, which means du is 4x dx. So we need a 4, a 1, 4, and it would be 1 over 4, integral 4x dx is du, and that's u to the 1/2 at the bottom, u to the negative 1/2. Now, limits are the x values when x is between 0 and 2. It's like doing an area, if it's an area where x is between 0 and 2. Now we have u, the variable, so it's not 0 and 2 anymore. You have two choices here. You plug values of u, meaning for x equals 0, u is 1, and for x equal 2, then u would be 9, and then you can plug them in, or you leave it, you bring them back when x is, and that's what I usually like to do. So 1/4 u to the negative 1/2 is, you add 1, you get u to the 1/2 divided by 1/2 or times by 2, so it's 1/2 square root of u, and u is 1 plus 2x squared. And now we bring the limits back because now x is back. So we do the upper limit, so 1/2 square root of 9 minus 1/2 square root of 1, which would be 1. 3/2 minus 1/2 is 1. Here's another example, 58, page 426. Integral of sine of x cosine to the power 4 of x dx. So if we let u equal cosine x, u by dx is negative sine x. That means du is negative sine x dx. So dx, we need a negative, that's du, and this is u to the 4. So we need a negative here. So we get negative integral of u to the 4 du. So negative u to the 5/5 plus c. No limits to plug in. So negative cosine to the 5x/5 plus c. 66, page 426. So the definite integral from 0 to 1 e to the x over 1 plus e to the 2x dx. So if we let u equal e to the x, then du is be e to the x dx. So this would be du, and that would be u squared, and that's going to be arctangent or tangent inverse. So this is going to equal integral of du over 1 plus u squared. Notice I skipped the limits now, so it's tangent inverse u, which would be tangent inverse e to the x. Now I bring the limits down, back, so it's tangent inverse of e minus tangent inverse of 0 is pi over 4. Okay, last theorem of this section, integration of even and odd functions. Integration of even and odd functions. Let f be integrable over the interval from negative a to a, then, so it's negative a to a, like negative 2 to 2, negative 3 to 3, negative 5 to 5, that's the interval we're using. The integral from negative a to a f of x dx is twice the integral 0 to a f of x dx if f is an even function. And remember, even functions have graphs that are symmetrical about the y-axis. So if you're doing, this is an even function, f of x equals x squared. If you're doing from negative 5 to 5, negative 6 to 6, whatever, if I'm this area, then you can take 0 to a and times it by 2. That's what this is saying, okay? Which makes a lot of sense. The second part, the integral from negative a to a f of x dx is 0. You don't have to do any work to say if f is an odd function. Again, an odd function is symmetrical about the origin. Is symmetrical about the origin, like f of x equals x cubed. That's an odd function, symmetrical about the origin. So if I do integral from negative a to a, you can see why it's 0. That's going to give me negative value, equivalent positive. When you add them up, you get 0. So for example, integral from negative pi over 2 to pi over 2 sine x. Cosine x is 0, since f of x, which is sine x cosine x, is an odd function. It's symmetrical about the origin. And that's it for all of chapter 5. We're done with chapter 5. So let me stop there.